Students, so today we are in lesson 2 of digital communication. In last lesson, we have discussed that in digital communication, first analog signal has to be converted to a digital signal. And this conversion, although this conversion has some difficulties, so it's not as easy as it primarily looks like. And for that, towards that goal, we shall today first discuss the basic theorem, which is called sampling theorem. In sampling theorem, there is a statement, is empty is a band limited signal. Now, what is a band limited signal? That signal will have all many frequency components, but there is a limit to these frequency values. That is, it is band limited. It's not spread up to infinite frequency. If it is a audio signal, if it is a speech signal, then frequency may be limited to at the most 6 or 7 kilohertz. If it is a song, it may be up to 10 kilohertz. If it is a classical music, maybe up to 15 kilohertz, like that. So it is a band limited signal, not infinite frequency. And the name of the signal we have given MT, the function of time, and its bandwidth is FM. That means the maximum frequency of the signal is FM. And if MT is determined as regular intervals, that means you do not measure the MT continuously. You measure it only at some regular intervals of TS, time TS. It's like that when you have a fever, you do not put the thermometer in your mouth 24 hours. You measure it only at some regular intervals. And with those interval values, measurements, when you show it to a doctor, he can determine what your disease is actually. Similarly, here also, if the signal is measured, although the signal itself is basically continuous function, but if you measure it at some regular intervals, then those measurement values, it says here, this is in the theorem, the samples uniquely determine the signal. That means those values can uniquely determine the complete signal and may be reconstructed from these samples without any distortion. That means from those samples, the signal can be completely reconstructed. How? Let's say sampling period is Ts, or sampling rate or frequency is called 1 upon Ts or Fs. And the scheme is like this. It is very simple. The signal is multiplied by a sampling function. Sampling function is a regular train of pulse. It's a regular pulse train. This is a regular pulse train where the signal is to be measured and the multiplier output is STMT. This is a signal, continuous signal. This is a sampling function, which are a train of pulses. These are the pulse points where the signal is to be measured. And I have taken for convenience its amplitude to be 1. It could be anything, doesn't matter. Then, if these two are multiplied, you see the measured values will be like this. That means wherever is the signal, negative or positive, whatever is the value, will be the value of the sample, right? Then, this result, this figure that you are seeing, this result, when you go into the mathematical expression, this result very much depends upon this function ST. Now, you may ask, what can be the problem with ST? Problem with ST is, we have considered here in this picture a pulse of zero width or negligible width. But electronically, you have already understood a zero width pulse is not possible. And electronic signal will have certain width. Maybe it is very, very small width, but it will have certain width. And the nature of that pulse train will determine the output STMT. Now we go into a mathematical expression. This is the ST, which is a series of pulses at time Ts, 2Ts, 3Ts, etc., etc. Amplitude for convenience, I have taken 1. Now, the Fourier transform of this pulse train is like this. It is 1 by Ts, then it's a DC component, then 2 by Ts into cos f 2 pi fst, or you can say omega st. That means it's a cosine function, sinusoidal function. This is a sinusoidal function of double frequency, 2fs. This is a sinusoidal function of treble frequency, 3fs. And this series is infinite. This function is multiplied by mt. The multiplication, of course, is like this. STMT is equal to multiplied by 1 by Ts plus 2mt multiplied by this, and then the cosine function, etc., etc. It's an infinite series. Now, if you look at this function, output, product, then what you find, the first term is just the signal multiplied by a scalar, some amplification factor. They don't bother about the scalar. You have always an amplifier. You can amplify the signal MT to your choice, whatever you want. But first term contains the signal. What is the second term? Second term is a signal multiplied by a cosine function. This is a signal MT multiplied by a sinusoid. Now, this will produce two sidebands centered at Fs. It is like this. MT, signal MT has many sinusoidal functions in it. Let us consider any one sinusoidal function. Let us say any one function is cos omega t. Then when this cos omega t is multiplied by cos omega st, then you have got two cosine functions, cos omega s plus omega ct, and there is another function cos omega s minus omega ct. That means it creates two separate frequency components. One is omega s plus omega, another is omega s minus omega. Now, MT has many such frequencies. So altogether, it will create a band on the left-hand side of Fs and another band on the right-hand side of Fs. It's like this. If it is, say, original baseband signal MF in MT, different frequency domain is like this up to FM, and let's say this amplitude at various frequencies varies like this. Then product Vt is the baseband signal MT multiplied by some scalar. Then the second term produces a right-hand sideband or upper sideband and a lower sideband, extended from Fs to Fs plus Fm and Fs to Fs minus Fm. Then a third term, which produce similar two sidebands centered at 2Fs. 2Fs similar to sidebands. And it is extended up to infinity. But this is the baseband signal, albeit multiplied by a scalar, but this is the baseband signal. And it is a frequency domain signal. So it is clear that if we have a filter here, let us say the cutoff frequency of the filter is more than FM, but less than Fs minus Fm. That means cutoff frequency of the filter is something like this. If it is like this, then all upper frequencies will be discarded from the signal. discarded by the filter, and the filter the lower frequency. So, what do we find? The original signal MT can be fully recovered. Original signal MT can be reconstructed by simple low-pass filtering of the sampled output. This is basic sampling theorem, right? Here, there are two corollaries we have to mention. Suppose sampling frequency Fs, that means this frequency Fs, is less than 2 FM, then Fs, this left hand end, Fs minus FM frequency, it is below FM, so it will overlap here. So kind of overlapping occurs. That means here, if you cannot correctly recover the signal because there is an overlap of some other unwanted signals, right? Critical condition is when Fs is just equal to 2 FM. Then this is the critical sampling rate is 2 FM. That means critical value of sampling rate is double the baseband limiting frequency FM. But practically you cannot do it like this. And by the way, this rate 2 FM is called the Nyquist rate. Nyquist is a famous engineer and scientist in communication theories who brought in many complex communication theories and really made the life of communication engineers very, very difficult. So anyway, this rate is called Nyquist rate. That means what is Nyquist rate? If you have a baseband signal of 10 kilohertz, then Nyquist rate of sampling is 20 kilohertz. And of course, actual sampling has to be done at much higher rate because if they touch each other, then if you put a low pass filter here, filter does not, the spectrum is not rectangular. Filter frequency spectrum is always, there is a slope or droop. So whatever filter you can use, some unwanted frequencies will come into. So we always keep a distance between Fs and FM and 2 FM and Fs, so that the filter can filter it out here like this, right? In fact, I'll tell you, nowadays the standard sampling rate of voice sample, when we talk over telephone, standard sampling rate is 64 kilohertz, whereas our voice frequency is not more than 5 kilohertz or 6 kilohertz. In some cases, it may be 10 kilohertz, but not more than that. But standard sampling rate of voice and speech and song and music, etc., is 64 kilohertz. As a huge gap is left, so that you can design a filter appropriately. So this is basic sampling, and this kind of a sampling function, where we consider that measurement is done instantaneously. That means the width of these pulses is 0. This sampling is called instantaneous sampling, and these are the equations. But next we shall see natural sampling, because instantaneous pulses cannot be produced. You cannot produce electronically any pulse which is instantaneous, right? You cannot produce that. So we shall go to that natural sampling next day. Okay.